Okay, so welcome back. Hope reading week was fun. We have an exam next week. So this week we start something new, and we're looking at the rigid body portion of the course. So up until now, we've done everything you need to do in particle kinetics and kinematics. And we're going to do exactly the same thing, but now for rigid body kinematics and then kinetics. So kinematics this week and part of next week, and then for the next 8-10 lectures, I forget how many, we have additional material to cover on the kinetics. So we do second law, work energy, and momentum. So today what I'm going to do is define the motions and remind you that because it's a rigid body, everything has both size and mass. So particles, no size, but they have mass. If you look on Quarkus, you can find this material for me from 2022, lectures 19 to 24, maybe 23, I'm not sure right now. But the OneNote module, Rigid Body Kinematics from 2023 is also up. Okay. Yeah, I don't like that. So I can define anything I want as a rigid body in the sense that a rigid body is just going to be treated as a mass with a whole bunch of particles. So those little red spots are all particles that make up an entire body. And all it is a mass distributed in space. Where it gets a little bit weird is when we start talking about the three different types of motion. Oh, other thing. This is important to remember, but it's not really that it's not that concerning. Newton's second law, which was sort of the bulk of everything you did in chapter 3 and 4, is really applicable only to particles. We're going to be switching to Euler's laws, or Euler-Newton laws, but they're essentially the same. So I have a mass distributed in space, I have these little red spots that all represent particles, and I have a whole bunch of them that describe a rigid body, and they're sort of contained geometrically. So I have three different types of motion that come out of this. The first one is translation. And here I have a body that I have point A, point B, point B, point A. On the left is the position of the body at time 1. On the right is the position at time 2. And I can have two different types of translation that are kind of important here. I can have rectilinear translation. And that kind of motion occurs where you have straight line motion. So the motion is, the particle is translating from A to B. These two lines are very nice straight lines, by the way. A, B just moves this way. And so the body never rotates. It stays in the same orientation, and it just moves as if it's just rigidly held in place. You can also have curvilinear translation. And here, the motion is curved equidistant paths, which means, again, the particle travels along a curved path, but the orientation of the plate, or whatever mass I'm looking at, doesn't change. It just sort of moves up and down, does whatever, but it doesn't rotate. And you can guess what the second type of motion is going to be. So here I have two particles again, A and B, and they are going to end up having travel or paths that are circular. And you've been dealing with this a little bit when you've been looking at angular motion. So you've calculated omegas for a number of different things already at this point in the course. This is sort of taking all this together. The last kind of motion is going to take these two types and here, the particle, or the rigid body sort of has some shape. A, B, and it ends up at some other location with a completely different sort of B. Okay. So however it happens, but basically what you're doing with this type of motion is combining rotation and translation. And that's how we're going to end up solving them. So let's look at a rigid body and see how we deal with it and what that implies to all three of these types of motion. We haven't done any calculations yet, but right now we have these three motions. So we have a translational motion, no rotation of the body, nothing changes in orientation. A rotational motion where it doesn't translate, but it rotates. And then finally, a general plane motion where it both rotates and translates at the same time. And your goal is to try and simplify that motion in a way to make it doable. So I have an object, it has a point A here and a point B, and let's say we have V sub B here and V sub A. So we have objects that can have different velocities at different points in time and different velocities in terms of both magnitude and direction. So this is probably something that's rotating in a weird way. And as it's rotating, the distance between these 2 points is defined as R of B with respect to A. So if you remember back in chapter 2, when we were talking about relative velocity, I mentioned that it's not really useful with particles. Here, it is the foundation of everything you're going to end up doing. So this is crucial at this point. So if we go back and we're starting to look at that motion, our goal really for all rigid body motion, and I'll use RB regularly, is one, motion of a single point, and two, so if I look at that particular body right now, this one right here, I can also, that color, define a unit vector, EB with respect to A. So EB with respect to A is just a unit vector that points in the same line as RB with respect to A, and it describes the direction of B with respect to A. And where I start from in all of this, I can say velocity of B equals velocity of A plus velocity of B with respect to A. And I can say the other thing, which is RB with respect to A is RB with respect to A magnitude, EB with respect to A direction. All I'm doing here is using a unit vector that describes the distance between the two. Later on, of course, we'll start to separate that out a little bit, but this is helpful for a quick derivation. So VB with respect to A is equal to d dt of RB with respect to A EB with respect to A is tunk, tunk. Okay. And of course you can sort of break it down a little bit further and say that that is equal to d dt of the magnitude of RB with respect to A, EB with respect to A, plus RB with respect to A magnitude, EB with respect to A dotted. And I don't need a ddt there. I need a ddt on this. Okay. So all I'm doing is chain rule, calculating derivative with respect to time of RB with respect to A. Now, the magnitude of RB with respect to A, which this is 0. It never, or the rate of change of RB with respect to A, the magnitude is going to be 0. It never changes. It's on a rigid body. It's never going to change its length. So I can get rid of the first term. So VB with respect to A becomes equal to RB with respect to A, EB with respect to A dotted, which is equal to, from other work that we did, omega AB crossed with RB with respect to A. Okay, that's kind of useful because now I'm trying to describe something. I have two terms that I got to worry about at the very top. I have a translational term and I have this one, which is confusing, but based on this, it's a rotational term. So that discussion at the very beginning when we started to talk about general plane motion, now I have something that kind of makes sense. It's sort of a translation plus a rotation. And I can write that now as VB equals to VA plus omega AB crossed with RB with respect to A. And I'm going to write this right now as a vector form. So we're going to do a lot more vectors calculations. The other thing to remember is that omega is equal to theta dot. We've used theta dot a lot in this course where you had d theta dt, the rate of change of angular position. Now we're going to switch that and we're going to end up using omega mostly for these terms. The other term that will appear, and that's not quite yet, but within a lecture or two, is that alpha, the angular acceleration, which is theta double dot, second derivative of theta with respect to time, is going to be alpha. All right, so I have VB, which is now equal to translation plus a rotation. And that's my general plane motion. Go ahead. This one right here.
Yes.
Yeah, I don't really want to do this derivation again. So I've done the derivation in a form back in when we were doing the unit vectors in chapter 2. So if you remember the unit vectors, you'd end up with these extra terms and you'd end up with theta dots and you'd end up with all these terms. So I'd rather not go through all of that because it's tiring and it doesn't help you very much. But the main point is with that is that this term deals with the rate of change of direction. And because of that, you end up being normal to it. And so that's where you're ending up with the omega Okay, general plane motion, all of that. So, speaking of alphas, I can finish the entire chapter in about 2 seconds here. If you take the time derivative of velocity with respect, or the velocity with respect to time, you end up sort of coming up with terms that kind of look familiar, which are acceleration of b equals to acceleration of a, that's easy, plus omega ab dotted with rb with respect to a plus omega ab cross with rb with respect to a, and that's dotted in there. Yeah, don't need to do that. So now I have an acceleration term, and it's the same sort of thing. I have a term that deals with the translation. Still, that's still there. I have this, and I have this. Now, this term right here is the time derivative of angular velocity, which, unsurprisingly, is going to be alpha, that new alpha that I just said you didn't have to know in this lecture. But then you have this last term, rb with respect to a dotted, where you can rewrite this as omega ab cross omega ab cross rb with respect to a, tuck, tuck, like that. Okay. In this course, all motion occurs within the plane. So typically at this point, we're not going to talk very much about NT or R theta systems. We'll talk about XY, and we'll have XY within this plane. All rotation is occurring out of the screen. And so as the rotation is occurring out of the screen, you can write this term as 0, 0 omega, cross with 0, 0 omega, cross with rb with respect to ax, rb with respect to ay, and 0. And I tend to write it this way because I want to break it up into parts. And when you write it that way, one thing that you notice is that you have two terms that are dependent on k, and one term that has I and j in it. You'll have different sort of variations on this, but what you find for this course and this last term ends up being minus omega squared r. So when I look at my governing equation, or the equation I'm going to end up using, it becomes acceleration of b equals acceleration of a plus alpha ab crossed rb with respect to a minus omega squared rb with respect to a. So those are my two governing equations. We won't deal very much with this yet. If I have time, I may do an absolute motion problem, but I'm not going to really go through this equation yet. This equation we'll talk about more in the next couple of lectures. So what this means is, this is the kind of motion that we're looking at. So I have an object, it has A, it has B, and I know for some reason velocity of B. And I can say that velocity of B, and I don't want it that way. Ooh. I can say that that rigid body now has a velocity. I don't know velocity of A, I know velocity of B, but I can tell you that velocity of A is going to be the summation of a translational component, same body, B, oh, no. Sorry. Keep flipping directions on this. Velocity of A, velocity of A, tunk, omega AB. It's going to be a combination of both the translational velocity of A, whatever that is, plus a rotational velocity to align it with what I expect to have happen. And so I'm trying to calculate the omega of the body, the angular velocity of it, plus its translational velocity, and I get velocity of B from it. Now I can do the same thing for acceleration. But accelerations, as you can imagine, become much more difficult. So again, same thing as before, I want to write this in terms of acceleration A. But I have a problem. Because this is rotational, I'm going to end up not being able to do everything exactly as I had hoped to. So I have to figure out what the acceleration of B with respect to A is. Ugh. In the tangential direction, and the acceleration of B with respect to A in the normal direction, in order to extract out an acceleration of B with respect to A, whatever that is. So it doesn't matter. This is more graphical representation, but it's the problem that's going to have happen, or you're going to face, is how do you describe these kind of motions. So you have that above. In the sense that you have the tangential and normal components there, but you have to add everything together. So if we go back and we start with the translational, we have an object that's sort of going in space. And a direction and all of that. But RB with respect to with translation does not change orientation and it doesn't change magnitude. So that means that velocity of B, which equals velocity of A, plus omega AB crossed RB with respect to A, and I'm putting all the vectors in because I don't, this goes to 0. Because there's no rotation. So this thing just sort of moves along. It covers a direction and a path, and as it's moving, it's going to have the same velocity any point on the body. If it didn't, and you sort of thought it was translating, it would sort of tear the body apart, right? Because you have to have, but it also means that acceleration is equal. So you take the derivative of that, everything is easy. So the best in terms of intuition is going to be translational motion, because you can always say, okay, yeah, I got rid of that term, I have these two terms, or I have these two terms. Everything works out really nicely. So you could have something where you start out at a theta and you displace d theta, but it's rotation. And this is where we start to sort of get into new stuff in terms of notation. And angular position is just going to be theta. Angular displacement is going to be d theta. And you start out with angular velocity, which is theta dot d theta to dt, or omega. And omega just, again, looks like a W. Go ahead.
I'm sorry, the angular displacement, wouldn't it be theta plus d theta?
Yeah, I'm just sort of showing a displacement. So d theta is just a displacement. So total displacement would be theta plus d theta in the end. And you end up with a whole bunch of terms here again, but there you go. Acceleration becomes more difficult. Now, the acceleration term that I had before, if I have, say, again, a point A and a point B on a rotating system, I can go back to this equation up here and just say VB equals VA plus omega cross RB with respect to A, and I'll end up just getting rid of that term because there's no linear translation. And so often I will have rotation, and rotation will be chosen such that I have some sort of, well, maybe not in that case, it's not 0. Let me choose A so I'm getting a 0. it's rotating about this point. So A. So if it's traveling in circular paths and I've chosen the right point, I can just sort of put everything there and describe it in that form. So VB equals omega cross RB with respect to A if A is your center of rotation. It also becomes really interesting because this simplification of that equation ends up being one of the techniques that we use in the course in order to solve these types of problems, and that's a center of zero velocity. And so you're going to be looking for centers of zero velocity in order to solve these problems. Yeah, I keep forgetting that I need to solve problems with absolute motion. Yeah, all right. There are a number of different ways to do things. I'm going to show you a method that you can use for rolling and rolling without slip. But rolling without slip is going to be one of the important sort of considerations that we have. And the first technique that I'm going to use is something called absolute motion. And so with absolute motion, it's section 5.3. We do cover it in the course, but we then ignore it for the rest of the course. And I would actually recommend not using it unless you absolutely had to, which I don't know, that's up to you. All right, so absolute motion, the idea is that we can use the geometry directly. And we can use the fact that here, for example, I have a problem. A wheel of radius r that rolls on a flat surface without slipping. Determine the angular motion of the wheel in terms of the linear motion of the center O. So this is the center. Also determine the acceleration of point on the rim, so somewhere out here. And as the point meets the surface on which the wheel rolls. This is not the motion that you would see, but it's sort of, I couldn't do much better when I was drawing it by hand. But you start out with a point in contact with the surface at time 1, and at time 2, this thing is going to roll, and as it rolls in a clockwise direction. And because it's rolling in a clockwise direction, C at time 2 is going to be displaced to a point C prime. So point O and O prime are going to be straight lines, or straight line connections, because there's no motion up and down of the center. Any other point on a rolling body will rotate. You have V naught, A naught, you have omega and alpha, omega again, theta dot, alpha, theta double dot. Ew. It's good for simple configurations. That is, you have simple configurations that are pretty well defined. You're just using geometric relationships to get the motion. Everything works out really nicely. And this warning is actually useful for the whole remainder of the course. In the first half of the course, we often, I would say, hey, counterclockwise, right-hand rule, it's not, there you go, counterclockwise is positive, clockwise is negative. However, in this part of the course, and using the techniques you're going to see, it's really important to remember clockwise is negative, counterclockwise is positive. And you have to use the right-hand rule in all of these solutions to sort of make them work. So if I look at this, and I look at that distance between O and O prime, and I've defined that as a distance S. And that may not be clear. S. Right there. That distance, straight line motion, is going to be SR theta. Now, the other thing to remember, and it's really important to remember, is that when you have no slip, and we won't be checking slip or no slip right now, but we will in the next chapter, that velocity at point C, when it's in contact with the surface, is 0. So it's 0 velocity at point C. All right, so I know that S is equal to R theta. And if I take the derivatives of all of that, R is going to stay constant. So I get derivative of S with respect to time is V. So V of naught, it's going to be R omega. And if I take the derivative of that, again, R is constant, and I end up with R alpha. Units are consistent. Everything sort of works out reasonably well. So now I have to do the geometry. So I've defined here my x and my y. So the x displacement is going to be x minus r sine theta, and the y displacement, or y position, is r minus r cos theta. So my x and y position as a function of time of a point on the body is going to depend on how far I've displaced, and I look at the geometry of it, and I have here, that geometry right here. So I have x along this direction, I have y, I have to sort of consider what's going on there. So I take a derivative, or I can sort of rewrite that as r times theta minus sine of theta. X dot is equal to r theta dot 1 minus cos theta. X dot is equal to v naught 1 minus cos of theta. X double dot is equal to v naught dot 1 minus cos theta plus v naught theta dot sine of theta. X double dot is equal to a naught 1 minus cos of theta plus r omega squared sine of theta. Ooh. Same thing here, y is equal to r 1 minus cos of theta. Y dot is equal to v naught sine of theta. Y double dot ends up being a naught sine of theta plus r omega squared cos of theta. At theta equals 0, which was the condition where C is in contact with the surface, x double dot is equal to 0, and y double dot is equal to r omega squared. So this is a generalized form. It solves for everything at any point on the body. Everything is super. The problem with it is it's a big pain in the neck to do, and it's not, and I'm using this word very carefully, as easy to do on other bodies. So in this particular case, I can just define all the directions, all of the things, and for the case of theta equals 0 degrees, I end up with this. Now what's important too, and this is something to think about, is that I have a body with 0 velocity at the surface, point C, and it has 0 tangential acceleration, but it has a normal acceleration towards the center. And so one of the things that you have to keep in mind is this term right here. So you're going to see that a lot. Now, where this gets interesting, and I've taken this out of Merriam and Craig, is when you're dealing with different types of bodies, because different types of bodies have different points of contact. So here, for example, I have a zero slip occurring where the contact point is here. With a spool, it's here, and with an object that's sort of attached to a cord and it's dropping in space or rising in space. Again, same sort of thing. This point right here is a zero velocity, and this is a zero velocity. So you're going to see a lot of problems in this course where you deal with zero velocity or zero slip conditions. And this is one thing that you really should keep in mind as you're sort of looking at these problems. However, let's do this same problem, but use the approaches that we've sort of talked about already. I have a wheel, and that wheel is radius 300 millimeters. This time you get numbers. And what I want, it rolls to the right without slipping, and it has a velocity, v naught. Okay, it rolls without slipping, so there's a floor here. Calculate the velocity of point A on the wheel from the instant represented. Now, using the techniques I just did, I could define, again, a zero velocity, or I could define immediately what the velocity of A is. So, woo, there we go. So, starting there, I can say that velocity of O, or A, is equal to velocity of O plus velocity of A with respect to O. And I'm given in this problem the velocity of O, because that's straight line motion. Remember, again, the center doesn't rotate. It translates. And so V naught is equal to 3 meters per second, and it's to the right. Now, I know velocity of A is equal to velocity of O plus omega cross RA with respect to O. So translation plus a rotation. And when I do that, and recognize from just looking at this body, if V naught is equal to 3 meters per second in the I direction, and that's positive, and R C with respect to O is equal to plus 300 millimeters in the J direction, or O with respect to, no, RO with respect to C. C is plus 300 millimeters. Omega is going to equal to minus 10 rads per second in the K direction. And how do I know that? I can look at this. I have velocity of O. I have this distance right here. So that's my C, and that's my O. I have to have a rotation like this, which is clockwise. If it's clockwise, I haven't done any type of vector calculation, then it's going to be a negative value. So it has to be negative.